All right, so we're going to get through part of this today, so we have a short day. But the entire chapter is on logs. And logarithm, where the word log means the exponent in a problem. Mostly because you can take a log and express it as a power or an exponential form, and vice versa. So they're equivalent. This is something you should remember from Algebra 3-4. So all you do is take the base of the log, so this is log base A, whatever that base happens to be, of y, ladies, equals x. So to change it into exponential form, take the same base of the log, it becomes the base of the power. And then all you do is switch the x and the y. That's it. However you need to memorize that or learn it, just do it. You have to be able to go backwards and forwards. So let's take this, and oftentimes I'll just memorize one of these, and I'll put it into exponential form to test it to make sure that I'm doing it correctly. So if you get stuck and you kind of forget, I would remember log base 2 of a is equal to 3. Because if I put it into exponential form, what's the base of the power? What's the base of log? 2. And then we're just going to switch the 8 with 3. So the 3 becomes the exponent, and the 8 goes on the other side. Is 2 cubed equal to 8? Yes. Yep, so it's equivalent. You've got to be able to go backwards. So on this, with exponential form, the base is 3, bless you. So I'm going to take log, and I'm going to take the same base, 3, and make that the base of my log. And then you're going to switch these two. So the 9 goes over with the log, and the 2 goes on the right side. So you do 10 squared equals 100. Put that into log form. So you should have log base 10 of 1,000 equals 200. Oh, 100. Oops, I can't see. It's okay. Overly. All right. Your common log is always the LOG. Just because I stopped talking doesn't mean we start. And it always has a base of 10 if it's not shown. Very rarely do you actually see the common log of base 10 written with a base of 10. It's usually left out. It'll just look like this, log of 5. But if it's written that way, it's understood that it has a base of 10. It's your common log. Your natural log always has a base of e. E is this lovely number here. It's an irrational number. It's very similar to pi. And the symbol for natural logs is ln. And so the same thing, let's say the same thing with natural logs. Like you'll have the natural log of 5. Notice it's not written with a base, because it's understood that the base of all natural logs are e. What's the difference between a natural log and a common log? Not a whole lot. We'll explore their graphs tomorrow, but the graphs are nearly identical. One of the graphs is flatter than the other graph, but they're nearly the same. So let's look at some properties of logs. These are properties that you want to memorize, and the more you use them, the better you're going to get at them anyway. And to prove them, I'm going to take them out of log form and put them into exponential form. But anytime we have the log base anything, whatever this, it doesn't matter, 10, 50, whatever, it doesn't matter. If 1 is right here, if we're taking a log of 1, 100% of the time the answer is 0. And if I take that out of log form and put it into exponential, I've got a, because the base here is a, and then switch the 1 to 0. So a to the 0 is equal to 1. Isn't that true? Anything with a 0 power is always equal to 1. So anytime you take the log of 1, its value is 0. The next one, you're taking the log of any base of that same number. So if the base and the number you're taking the log of are identical, then the answer is always 1. And again, if I put it into exponential form, the base is a, switch the a and the 1, a to the first is equal to a. Isn't that true? So then the next one, what's the difference between these two? Yeah, they both have the same base and the same number that we're given the log of, but the second one here now has an exponent of whatever number, in this case it's x. So whatever that number is, that's what the answer is going to be. So whatever the exponent is, when the base and the number you're taking the log of the same, whatever that exponent is, that's the answer. Now if you look at this one over here, isn't the exponent of a to the first power? Aren't these really saying the same thing? That had an answer of 1. The exponent is 1. This has an exponent of x. Whatever the number might be, it has an answer of x. So if I had, oh, I don't know, log base 5 of 5 squared, what's the answer? Just 2. That's what that's saying. And so if I take this out of log form and put it into exponential, my base is a, and I'm switching the a to the x and the x. So the x becomes the exponent, and the a to the x goes on the other side. Isn't that a true statement?
So would you write that in Math Excel? What would you write? 1?
They would be looking for the answer of x, because they're going to give it to you like this.
So it's just
So
x.
they'll give it to you like that, and you just write the answer of 2. You're not going to have equals in it. Then we're going to go into natural logs. So none of these natural logs have a base, but all of these are exactly the same as what we just looked at. This is the base of this e, base e, base e. They're all base e's. Well, anytime we take a log of, it doesn't matter what the base is of 1, the answer is going to be 0. Why? It's the same thing for a common log as it is for a natural log. If I take this out of log form and put it into exponential, e to what power is equal to 1? It has to be to the 0 power. Same thing here. Notice that the base of the natural log and the number we're taking the log of are the same. Anytime those are the same, the answer becomes 1. Because the base of e to what power equals e? Has to be to the first power. And again, these two are really identical because I still have the same base and I'm taking the log, the natural log of the same number, but this time I have an exponent of x, so the answer is x. Same reason over here, that e has an exponent of 1, so the answer is 1. This has an exponent of x, the answer is x. So again, taking it out of log, my base is e, the x becomes the exponent, and the e to the x goes to the other side. So I get a congruency. Then there's a couple of others that you need to know that are not written on here. You can have a power, bless you, power with a base of e, and you can actually have a log in an exponent. Ellie, are you writing notes? Okay. Looks like we're splitting hairs. So let's say that I have the exponent natural log of x. The answer is going to be x. Note one thing though. Notice how this base that we can't see is automatically understood to be e. Anytime the base of the power and the base of the log are identical, so they both have a base of e, whatever you're taking the log of is the answer. The base of the power and the base of the log are the same. So let's look at it in common log form. What if I have, what's the base of the common log? 10. So if I had a base of 10 to my power, and I had the log of x, what's it understood that the base of this log is? The base of the log.
X.
No, the base of the log. What's the base of this log right here? 10. We can't see that. So again, I have the base of the power, the base of the log are the same, so yes, your answer is x. Well, what if the base is not 10? What if my base is, bless you, some number, we'll call it b? and I have the log of, the base had better be the same, base b of something, then it'll still equal x. So long as the base of the log and the base of the exponent, or the base of the power, are the same, your answer is going to be whatever you're taking the log of. So we're going to use some of those properties as we go along. I'm going to go through example 1. We'll see how far we get through it, and then we'll finish up tomorrow. So pay attention when you're doing your homework to whether you're to be solving it with a calculator or without a calculator. And so all of these are without a calculator. So as I go through and solve something, if it doesn't have an equal sign, I automatically set it equal to x. Because if something's in log form and it doesn't match one of the properties above, then I'm going to take it out of log form and put it into exponential form. So let's take this out of log and put it into exponential. So what's my base? 2. And then switch the 1/8 from the x. So I have 2 to the x equals 1/8. Then your goal is to make the left side and the right side both look like powers with the same base. So look at the numbers you have here. 2 is a smaller number. Can I make 8 into something with 2? 8 is 2 to the what? Third. So let's switch that out. So I've got 2 to the x is equal to 1 over 2 to the third. Well, I don't have a power equals a power. I have a power equals a fraction. But can I take that 1 over 2 to the third and just get rid of the fraction? Very good. I can put this up into the numerator. When I move that up into the numerator, I have to change the sign of the exponent. And so it becomes 2 to the x equals 2 to the negative 3. And using logic reasoning, if I have the same base, what can I conclude about the exponents? X has to be negative 3 as well. So my answer, x equals negative 3. Squeeze that in. Your whole goal is to create the left and right side having the same base. Let's do it again. This time I have log of 1,000. Immediately equals x. What is it understood that the base of this log is? 10. So take it out of log form and put it into exponential. What do you get? What's the base of your log? 10. Switch the 1,000 in the x. So 10 to the x equals 1,000. So look at your smaller number, 10. Can I convert 1,000 into something to 10? Yep. How many times are there in 1,000? There's 3 zeros, so it is 10 cubed. So we have 10 to the x is equal to 10 cubed. So now I have the same base. What do you conclude?
X equals 3.
Very simple, right? X equals 3. I can do this all day long. Love it, love it, love it, love it, love it. I feel like you're sick. All right. I know. I can tell that. All right, so this equals x. There's no equal sign, make one. Take it out of log form, what do you get? 27 to the x equals 9. Now the smaller number is 9. Can I convert 27 into 9 to the something? No. Okay, so here's, I can't do that. But can I convert 27 and 9 into the same number to something? Yeah, what can I convert 27 to? 3 cubed, right? But don't forget that that is still raised to the x power. So only the 27 got replaced with 3 cubed equals the 9 gets replaced with 3 squared. Remember your exponent rules. What do I do with the exponents when I have power over power? Don't subtract. What were you saying?
No, sorry.
Multiply. Exactly right. So I get 3 to the 3x equals 3 squared. So what's your conclusion? It's not quite so straightforward.
3x equals 2.
3x equals 2. So we still conclude that the exponents are equal. Essentially, I'm getting rid of those bases. And now solve for x, what do you get?
2 over 3.
Yep, x equals 2/3. See how I can do this all day long?
No.
All right, so this time I have an equal sign. So one of the things in the future that we're going to try to do is get a log on both sides of the equal sign that have the same base. So both sides have a log of base 7. Logically, what can we conclude about x? If I'm taking the log of the same base of some number and setting equal to the log of the same base of 9, doesn't x have to equal 9?
Yeah.
Logic says it does. So obviously those are going to get more difficult in the future, but that's one of the things we're going to strive to create. This one's a little bit more tricky, but what do you notice that it's missing? An equal sign. So I'm going to add an equals x. The very first thing I would do if I were you would be to get rid of the log. So put it into exponential form, even though you see that fifth root of 16. Put it into exponential, you get 4 to the what? X equals fifth root of 16. Then look at your numbers. I got 4 and 16. 4 is smaller. Can I turn 16 into 4? Yeah. So I've got 4 to the x is equal to the fifth root of 16 is 4 squared. Now I could have turned them both into 2. That just makes it a little bit more complicated. So, go to the lowest number. Don't go any lower than you have to. Let's go that way. So then let's review, how do I convert something that's underneath the radical into a base with a power? Or base with an exponent. Won't my exponent be a fraction? So I get 4 to the x is equal to 4 to the, whatever the 4 underneath here is being raised to, in this case a 2, that always goes in the numerator. Whatever your root is here, that always goes in the denominator. So I get 4 to the 2/5. Now we can convert. 2/5. X is equal to 2/5. Last one. Now the natural log of 4 on one side, the natural log of x on the other side, it is understood that the base of both of these is what?
4.
It's not very deep. And so don't I have log base e of 4, log base e of x, they're both the same log, both the same base, when you conclude about x. It must equal 4. And you think you're done? Why are you packing up? I have, one more minute. All right, so we'll conclude this tomorrow. But you can